Hello my friends, and welcome to this new section where you will finally learn on how to evaluate your regression models and mostly on how to select the best one. Alright, so this is indeed a section that has been long awaited because indeed in this whole part 2 of regression we built many machine learning models, and now most of you must have the question, okay, that's cool, I have all these regression models in the toolkit, but which one do I select? Which one should I apply for my dataset? And well, I actually have some very good news for you. We will give the answer to this exact question in this tutorial. So I'm going to try to reveal everything in this same tutorial so that you know this can be the ultimate tutorial of regression where you finally learn on how to use your regression toolkit the right way on your future datasets. So what I will do in this tutorial is I will introduce you to this toolkit that I've just made and which contains all the regression models we learned together into some very generic code templates. By very generic code template, I mean that you will be able to use these code templates on your future datasets by having only one or two things to change. I made them as generic as possible so that they can be ready to deploy on your datasets. And besides, each of them contains, at the end of the implementation, the evaluation tool, allowing to evaluate your model so that you can very easily and quickly compare the performance of each of them. In other words, in short, thanks to this toolkit, you will be able to select the best model for your dataset in a very short amount of time, very, very efficiently. And that's exactly what I'll prove to you, what I'm going to show you in this tutorial. We're going to take a real-world dataset, with several features and lots of observations. I will deploy each of the regression models of the toolkit on this dataset, and you will see how quickly and efficiently I managed to figure out the best model. And that's actually the answer to the question, how should I select the best model? And the simple answer is, try all your models. Try all your models and just select the best one having the best performance result. And that performance result is measured by, of course, the coefficient r squared or adjusted r squared. All right, so there we go. Let me introduce you to this toolkit and then let's proceed to the demo. But first, let's make sure everyone here is on the same page. This is a new folder, different than the whole machine learning A to Z folder containing the 10 parts. This is a new folder where you will get, that regression toolkit containing all the regression models, and then when we tackle part 3, that classification toolkit with all the classification models. And mostly, this is the model selection folder. This is the folder you will want to use when you want to deploy either your regression models or your classification models on your dataset in order to quickly and efficiently select the best one. Why do we need to do this only for regression and classification and not the other branches of machine learning? Well, that's because you will see that from part 4, each of the branch will contain only 2 machine learning models. And for each of these branches, from part 4, you will see that it will be very clear which one to choose. I will tell you exactly which one you must choose. But here for regression and classification, well, we have many machine learning models for each branch, so you need this model selection folder in order to have these toolkits both for classification and regression so that you can efficiently select your best machine learning model. Alright, so there we go. Make sure to connect to that link. That link was provided just before this tutorial in the article. And now, there we go. Let's enter this regression folder for model selection. And as you see, it contains our 5 regression models that we studied in this part 2. Multiple linear regression, and I didn't include simple linear regression, of course, because now we will work with a real-world dataset with therefore several features. Then we have polynomial regression, then support vector regression, then decision tree regression, and of course random forest regression. And as I told you, I made each of these implementations very generic so that you can deploy them on your future datasets by having only 1 or 2 things to change, assuming of course that your dataset has a CSV format and contains all the features in the first columns and the dependent variable in the last column. That's really the essential condition. And then of course here I chose a dataset without missing values or categorical data. That's because I trust you will know how to handle this thanks to your data preprocessing toolkit. So this dataset is quite classic, but yet real world, because as you can see, it contains several features and many observations. Actually, almost 10,000 observations. If we scroll down, yes, almost 10,000. All right, with, as you can see, only numerical values, no categorical data in strings, and once again, no missing data. And I chose such a data set so that, we can make our code templates for each of our regression models 100% generic, so that you only have to change the name of the data set. All right, and now what is this data set about? Well, that's a classic data set from actually the UCI machine learning repository, which I encourage you to have a look, because indeed it is a website that contains a lot of data sets on which you can practice. And this one is actually called Combined Cycle Power Plant, and it consists of trying to predict this dependent variable, which is actually an energy output. And don't worry, you don't have to understand how energy works or how the physics of this data set works. The only thing that you need to understand is that we want to predict this dependent variable, which turns out to be an energy output, and we are predicting this dependent variable with these 4 features here, which are first, the ambient temperature, second, the exhaust vacuum, third, the ambient pressure, and fourth, the relative humidity. All right, so that's only what matters here. You have to see it as, a general data set where you have several features that you're going to use to predict that dependent variable. And as you can see, the condition, in order to deploy our regression models on this dataset and the future datasets you'll be working on, is to have in the first columns the features and in the last column the dependent variable. All right, that's all that matters. If you have a dataset like that, which has no missing data and no categorical data, well, you can deploy each and every single one of these regression models by just having to change the name of your dataset. And if your dataset has missing data or categorical data, you just have to go to your data preprocessing toolkit to take care of this, and then you can deploy these models. All right, so now time for the demo. I'm going to show you how we're going to quickly and efficiently plug and play each of these regression templates by only having to change the name of the dataset, and then I'll show you how we will quickly identify and select the best regression model for this particular dataset. All right, let's do this. So our first step here will be to create a copy of each of these files, because these are all in read-only mode, because this folder was shared to you. So since all of you will access it, you can of course not modify it directly, but in order to modify it, you just need to create a copy in your drive. And to do this, well, we can just do a right click here and then make a copy. So we're going to do this for each of the regression models here. Let's do this. Make a copy for multiple linear regression, then make a copy, then random forest regression, make a copy, and finally support vector regression. And there we go. All right, good. So we made a copy of each of these regression models, and the copies should be either on your main drive or in this Colab notebooks folder. And well, as you can see, they are on my main drive, so you will actually very easily find them. And now what we're going to do is open each of these files in order to proceed with the demo. All right, so I open first multiple linear regression, then I'm going to open polynomial regression, in the same order as the one we used to build our regression models, then support vector regression. Once again, you can either open them with Google Collaboratory or Jupyter Notebook or even Spider Anaconda, because I also gave you the folder containing all these codes and the dataset right before this tutorial in the article. So then let's open decision trees. And finally, well, random forest regression. All right. So actually, let me put it like that, the same order. Support vector, decision tree, and random forests. All right, so now we have all our regression models open. I'm first going to show you the code templates one by one, and then we will deploy them on the dataset, and I'll show you how to quickly figure out which one is the best model. All right, so starting with multiple linear regression, let's see the different steps. So we start by importing the libraries. Of course, that's the first step of the data preprocessing phase. Then we import the dataset, And as you can see, I made it super generic, meaning that the only thing that you have to change is actually the name of your dataset here. That's why I specified in capital letters so that you can't miss it. Enter the name of your dataset here, and we will actually do that in a few minutes. Then here you have nothing to change, of course, because this automatically selects all the columns except the last one, therefore your features, and this automatically selects the last column, meaning the dependent variable. All right. Then we split the dataset into the training set and a test set. Of course, here that's very important to do this because since we want to select the best model, well, we need this test set in order to evaluate the performance of each of them, in order to compare it and select the best one. So we have to do this step absolutely. Then once we have, well, the training set, we will train our model on the training set. Then we will predict the test set results, to have a look at the predictions and compare them to the real results in y-test. And then finally, we will evaluate the model performance. And here, I don't want to scroll down now because we will discover together a bit later the code to evaluate a regression model, with the R-squared coefficient. All right, so that's the code template for multiple linear regression. And as I told you, and as you see, it is super generic because for any of your future datasets, provided that they have in the first columns the features and in the last column the dependent variable, and also provided that they don't have missing data or categorical data, well, the only thing that you have to change within this code template is just to enter the name of your dataset here. And that's it. By just doing this, you will be able to evaluate your model with a relevant metric. All right? So now let's move on to the next code template, polynomial regression. Well, here that's the same, the same data preprocessing phase with first importing the libraries, then importing the dataset where you only have to enter the name of your dataset here, and then splitting the dataset into the training set and test set. Then, of course, we train the polynomial regression model on the training set. So that's exactly like what we did in this part 2. When we built it, you recognize the degree equals 4. That's exactly the same code. Then we predict some test set results just to compare our predictions and the real results. And finally, we will evaluate the model performance, and I will reveal very soon how to do that. Okay, so that's for polynomial regression. Once again, very generic. You just have to enter here the name of your dataset, and then this code template is ready to be deployed. All right, then support vector regression. So here that's the same. First, the data preprocessing phase where we import the libraries, then we import the dataset, but then remember we have to reshape our dependent variable vector y because we have to feature scale it, right? Because we're doing regression. So the dependent variable vector has continuous numerical values, and therefore for SVR, we need to scale the dependent variable vector. That's exactly the same as what we saw together when building the SVR model. Then I added this, of course, in order to split the dataset into the training set and test set so that we can indeed evaluate the performance of SVR and compare it to the other models. Then, of course, we have feature scaling, compulsory for the SVR, with, remember, our two scalars, one for the matrix of features and one for the dependent variable vector. Then we train, of course, the SVR model on the training set. You know this very well, we did it together. Then we predict the test set results just to compare and have an idea of how good are the predictions of new observations. And finally, we will evaluate the model performance with R-squared. No worries, we'll get to that very, very soon. So that's for the SVR. Then for decision tree regression, well, exactly the same. The data preprocessing phase first with no feature scaling, right? Remember, we don't need feature scaling for decision trees. So once again, we only have to change the name of the dataset here. Then we split the dataset into the training set and test set. Then we train the decision tree regression model on the training set, exactly the same as we did in our implementation when we built it together. Then we predict the test set result in order to compare our predictions to the real result in y-test, and that's in order to have a first idea of the performance. And then, of course, we will evaluate the model performance with R-squared. And finally, we have the exact same data preprocessing phase where you only have to enter the name of your dataset here, and then we train the random forest regression model on the training set with the exact same implementation as how we did it together. Then we predict the test set results in order to get a first idea of the performance. And finally, we evaluate the model performance. All right, so as I told you, you have purely generic code templates which you can deploy for any of your future datasets as long as they have first the features and last the dependent variable, and as long as they don't have missing data or categorical data, in which case it's still fine, you can use your data preprocessing toolkit. But there you go, you have this code template, and now I'm going to show you how to evaluate your regression models using the R-squared coefficient. All right, so let's start with R-squared, that final cell in each of the implementations, evaluating the model performance. Let's see how we're going to do this. Well, as I also want to train you on how to be independent in machine learning, well, we're going to pretend once again that I actually have no idea on how to evaluate the model performance of regression models, and therefore that I have to go to the documentation online to figure out how to do it. All right? I'm just training you to be independent and quickly find an information whenever you need it. So let's go to a new tab. All right, and then let's just type, because I'm going to show you a trick actually. Let's just type scikit-learn. Scikit-learn, just scikit-learn, and then let's go to the first link. And you will be on the welcoming page of scikit-learn, which by the way looks super nice. And then I'm going to show you something very interesting. I'm going to show you the whole API of the scikit-learn library. The API is the whole library containing all the modules and inside all the functions and classes. All right, so these are all the modules starting from the base one, and the one I actually want to show you right now is the metrics module. The metrics module, which we'll find by scrolling down a bit more until we find M. Should find it very quickly. There we go. Scikit-learn metrics. All right, so as you might guess, this is the module that contains all the metrics of machine learning models, which therefore include classification models, which we will see in part 3, and what we are interested in now, the regression models. And in the regression models, here are the metrics. Let's have a look. Well, you have many of them. You have the explained variance score, the max error, the mean absolute error, the mean squared error, the mean squared log error. You have many of them. But the one we will use now, after Kirill's intuition lecture, is, of course, the R-squared. The R-squared score, which is, of course, the coefficient of determination regression score function. Okay, so there is not the adjusted R-squared, but that's totally fine. The R-squared is fine. You will perfectly be able to evaluate the performance and mostly compare the performances of your regression models to select the best one. So let's click this metric here, and we will find, well, the name of the function, which we will use, there you go, to measure the R-squared coefficient for each of our different regression models here. And that's exactly what you have at the end in this last cell, which I didn't want to reveal until now. That's indeed the R2 score function, which allows to evaluate the model performance of your regression model with the R-squared coefficient of determination. All right, so you have the same in each regression models, R2 score, right? R2 score here as well. That's exactly the same code actually, because I made these code templates 100% generic. So there you go, you have the R2 score function measuring the coefficient of determination, meaning the R-squared. And still in the assumption that I had no idea on how to implement the R-squared score, well, here what did I do? I actually went to the examples, and there you go, I just took this line of code, which clearly means that we're measuring the R-squared score between, the vector of real results and your vector of predictions. So I just took this, and then of course I took this before in order to import, of course, the R2 score function from the metrics module from scikit-learn. And so that's why, in each implementation, that's exactly what you see here. I import first the R2 score function from the metrics module by scikit-learn, and then I call this R2 score function on y-test, which contains the real results, the real values of the dependent variable in the test set, and y-pred containing the predictions of the same observations in the test set. All right? So that's only what you would have to do in order to figure out how to, evaluate the model performance of regression models, right? So that's why I really want you to have the reflex to look at the documentation and quickly find the information you need. All right, and now, my friends, time for the exciting step. I'm talking of course about the demo. So let's just take a quick little break and we'll start directly in the next tutorial.